Welcome, Calculus AB. This is for AP Calculus AB, which is really like a semester 1 college calculus course. Looking at Chapter 1.1, we are going to do three things today. Well, really, let's not talk about the calculus versus pre-calculus. We've already done that. Let's look at just tangent line problems and area problems. And maybe you're asking yourself, well, what is calculus? Calculus is the study of how things change if we really want to simplify it down. So calculus provides a framework for modeling systems in which there is change. Two of the founding fathers of calculus were Sir Isaac Newton and Gottfried Leibniz. Both developed calculus rather independently of each other, though simultaneously, but yet separately, as this says. And they described calculus that helped solve problems in physics. They both were doing it independently. Leibniz was the one that published his book first before Newton, but Newton came in like the next year. So this was like late 1600s that they did this. So they're both credited for finding calculus. So take a look at what the graph is showing here. You can follow the curve, and we've got a tangent line following the curve. If you notice that dot and the line, it's just always touching it at one point. That is one of the things we want to look at today, is what are tangent lines, which you learned about in geometry. And if we try to draw in our best tangent line here, it would look something like that, where it's just barely touching the circle. That's very similar to what you did in geometry. Picture number 2, try to pick your best spot to draw your straight line in, and I'm going to head for that area right there. Picture 3, try it yourself, draw it in. And picture 4, I would come in along the bottom like that. So 4 different tangent lines. Calculus involves a lot of looking at the slope of a tangent line at a particular point. And that brings on some problems of its own, because what do I do at a point to calculate slope? We're very familiar with slope calculations. It's something that we begin learning when we are in algebra. Slope calculations would look like the difference of y. You're familiar with like y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Another way we've seen this often is delta y over delta x. Delta being the Greek letter for change. So the amount of change in y over the amount of change in x. Another way we've often seen this is rise over run. The vertical change over the horizontal change. Notice I've misspelt rise on purpose. The y's are on top in the slope calculation. So taking that idea of slope calculation, how do I calculate the slope at point P so that I could tell you what the slope of this tangent line is? Well, that's a really interesting question, isn't it? I am very familiar with calculating slope when I have 2 points. 2 points, I can connect them up, and that gives me my y sub 1 and my y sub 2, and I can give you a slope of that. So how do I do it with 1 point? Well, the idea that we're going to develop is, well, what if we allowed this point Q to travel along that curve and get closer and closer to P? Well, that would mean then that my slope is getting closer and closer to approximating the real slope of my tangent line at point P. Many times what we're going to be asked to do is write the equation of the tangent line. So do you remember how to write equations of linear functions? I want you to try to think back to point slope form. It's y minus y sub 1 equals m, the slope, times x minus x sub 1. One of those, this will be just key. We'll use this all year long. Rather than the formula that you're probably a little bit more familiar with, y equals mx plus b, where we called that slope-intercept form. Okay. So, given a function f and this point P, find the equation of the tangent line, and we were talking about how this has its difficulties. So what I'd like you to do, let's go ahead and draw in this tangent line, or not the tangent line, the secant line connects 2 points, this point Q here with my point P. And what I had to do there, so there's some x value right here that's associated with my P value, right? And I noticed here that you use C, so I'm going to use C as my placement on the horizontal axis here. There's a point Q here. If I follow that down, that would lead to some new point on the x-axis, wouldn't it? A new coordinate. Well, as I travel over to this point, I'm picking up some change in x. So I could really call this C plus delta x. The output, when I put it into my function, I would have the coordinate pair C plus delta x, comma, f of C plus delta x. Input, right, my x value. Output, my y value, which really is representing height, isn't it? The height of the function at that point x. And from this, I can generate the slope of my secant line. So here, my second point, my y sub 2, would look like f of c plus delta x minus my y sub 1, f of c, over x sub 2, right there, c plus delta x minus my x sub 1 value, which is c. This simplifies nice on the bottom, doesn't it? C minus c makes those cancel to 0 or add up to 0, and that leaves me delta x on the bottom, and then I've got the difference of the y values up on top. And there we have the slope of the secant line. What happens if I draw in a few more secant lines? If I allow that point Q to move closer into P? Well, that would look like is, let's just take Q, slide it along the curve. I'm following my function, and I'm bringing this in closer and closer and closer. Well, that's just going to generate new secant lines, isn't it? And bring Q in a little bit further until I get it practically on top of P. I've now got P and Q really, really close. And notice how this slope and the actual tangent line are getting very, very close to each other. They approximate each other. And that is the idea in calculus, is that we allow Q to become very, very close to P. And as we move Q through this function and get it closer and closer, well, then our secant lines begin to approximate the slope of the tangent line. Okay? So take this problem here. Given the function f of x is equal to x squared, estimate the slope of the tangent at x equals 1. Notice here each successive point gets closer to the point 1, 1. So first let's graph f equals. So y equals x squared. Well, we all know that's a parabola centered at 0, 0. If I put in 1, I get out 1. If I put in 2, I get out 4 because I'm squaring it. And since this is an even function, notice the degree, it will be very symmetrical about the y-axis. So there is our parabola. Now, what I've asked you to do is please estimate the slope of the tangent line at x equals 1. Okay, let's draw in that tangent line. Here's the point 1, 1. Well, the tangent line would, that looks pretty good. Estimate it to just slide by the curve there at that 1 point, 1, 1. When I put in 1, I get out 1. Now, what I'm going to do is fill in this chart, because what I want to do is get close. Let Q, remember Q, some point, let it travel closer to this point P. If I put in 1.5 and square it, I'm going to get out 2.25. If I put in 1.1, well, that's like 11 squared. 11 squared is 121. Move the decimal point twice, I'm at 1.21. If I take 1.01 and square it, I'd have 1.020. And if I'm really getting close to 1, I'm greater by 1,000th, I would end up, put 1.001 in, square it, you come out with 1.002. Well, my best estimate of the slope at point P would be where my Q value is tightest to P. And the place that it's tightest to P is at this location. So I'm going to use the ordered pair 1, 1. And I'm going to use the other ordered pair of 1.001, comma 1.002 for its y value. Okay, that means that I can calculate a slope. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. If I subtract on the top, I'm left with the 0.002. If I subtract on the bottom, I'm left with that. If I multiply them both by 1,000, I'm left with that, and that gives me 2 over 1, gives me a slope of 2. So I now just discovered that I think the approximate slope of my tangent line is 2. I can write the equation. My best guess for the equation would be, well, I wanted to be centered at that point P, which was 1, 1. I just analyzed the slope and said it's approximately 2. Go into point slope form of the equation. Remember, it looks like this. You can look on your notes above where we wrote it down earlier. Fill in the information. And this is my tangent line equation. Pretty easy to follow? I think so. Next, let's talk about area problems. In calculus, we're going to try to calculate area underneath curved sections of functions. How can you do that? Well, on the limited knowledge that I have right now from my previous math courses, I'd say, you know what, pretty good estimate. I think I could just box this thing off, think of it as a rectangle, and I know the formula for a rectangle is length times width, and I could easily come up with this area. I'll call it A sub 1. That'd be a rough estimate. If I wanted to get a little bit better, perhaps I would chop this thing into 2 rectangles. So maybe I'll estimate the height of one of them right there. And then the other one I'm going to bring to a height of there. And now I'm going to calculate area of one, add it with the area of the other rectangle. So a little bit better using 2 rectangles. I could even get better. Maybe I'll go after 4 rectangles. I think I'll give myself some subdivisions here. I'll quarter it up. First rectangle, boom. Second rectangle, boom. Third rectangle, there. Fourth rectangle, there. Area 1 plus area 2 plus area 3 plus area 4 would get me my grand total. So even better if I used 4 rectangles. Continuing on, you know, you could chop it up into as many rectangles as you wanted to. I could even have these, couldn't I? And it would even get better. And notice how it's starting to follow the shape of the curve better and better. So, one way of approximating the area under a curve. Calculus, when we get into it in January, February, using integrals, we'll be able to do a much more accurate job of estimating area. So that leaves us with the homework, which we'll work on in class.